Hello to all from the Broadcast Center at VE7SCC, located on the VE7SCC facilities here in beautiful Coquitlam, British Columbia. We'll be carrying on a presentation here on high-frequency terrain analysis, and I'll just give you a little bit of an idea how things are going to proceed. We're going to have a bit of an intro into what the club is and what kind of facilities we have, and then I'll introduce our speaker, Adrian, VE7NZ, who will be actually presenting after having put together considerable effort on a presentation that I think will be very interesting for everybody. Just taking a second, we will be taking question and answers period after the presentation. If you could use the chat windows on both Zoom and YouTube, we'll track these questions, and at the end of the event we'll bring those questions up. If you're on Zoom and you do have a reasonable quality video, we will probably bring you up on the screen so you can interact with Adrian to ask the question, and if you have a follow-up you'll be able to ask at that time as well too. Those of you on YouTube, if you could put your questions into the live chat, we'll come to them each in turn, and Adrian will do his best to talk about them. For those of you that don't know what the Coquitlam Club is all about, we're located in a facility with about 4,000 square feet of building. In it we have an operating room, we have a maintenance area, storage, and a conference room, which is actually where we are right at the moment. Although you can't see the others in the room, it's capable of seating up to 20 plus people. We've been very fortunate to have this facility. It's on roughly about 4 acres within approximately 100 acres of a government property. It's on the Riverview lands. As I often say to people, Riverview was originally a mental health facility, a perfect place for ham radio operators. So we make good use of this facility. We have 3 towers here, each of them 80 feet. They're all self-supporting. On 2 of them we have what we call monster quads. They run 4 elements on 10 through 20, including the work bands, 2 elements on 30 and 40. The 3rd tower has a couple of Yagis on it. We have a TH7, which is fixed towards the Caribbean and South America. And then above that, at about 85 feet, is a 5-element monoband 20-meter antenna. And above that is a 6M7 JHV for 6 meters. Okay, we have also various antennas, which are wire antennas, trap dipoles for other bands, 40, 80, 160. In addition to that, in the operating room, we have operating stations for 8 people. We have predominantly HF, but we also do have VHF and UHF facilities. Incidentally, on each of our towers T1 and T2, we have antennas for VHF, UHF, including 220 meters, 220. So let's get into a little bit of a segue here. One of the things that we've tried to do is look at optimizing our antennas. We are beginning to get quite active in contesting, and it's always nice to know whether your antennas are optimally set up. Conventional wisdom says the higher the better. In fact, that's not necessarily true, and I think that Adrian in his presentation will probably reinforce that to the nth degree. It's really important to know the topology of the area that you're in, as well as the characteristics of your antenna, plus the antenna heights that you plan. For those of you that are planning on putting up towers and antennas, you may want to actually do the HFTA analysis and see what is optimal for your particular installation and also those areas of the world that you're interested in working. Adrian is someone I've known, as we were just saying, before he had sex. He was a ham radio operator at 15 years of age, and I'm happy to say that I knew Adrian at that time. He has been very active in the hobby and is currently trying to kick my butt in CWT every Wednesday, sometimes successfully, not always. I'm happy to report. But he does a pretty good job on CW, and he is very much an enthusiast. His background actually is quite interesting. He's worked extensively from a professional standpoint in satellite communications. He has held a variety of senior posts, including at the senior VP level with various companies. And at the moment, he's actually involved with a company that is working on GPS and the resolution of GPS to support autonomous vehicles, so self-driving vehicles, driverless vehicles. And you were saying, Adrian, I think that you're kind of working at this point to a 40 to 50 centimeter resolution, but in fact you've reached resolutions of 7 millimeters with the accuracy of the GPS, so quite an accomplishment. Okay, without further ado, I'd like to pass it over to Adrian, and he can give us a little bit of an idea of how things are going to go. So over to you, Adrian.
All right, thank you, Neil. Great introduction. This is the first time I've given this presentation, so I'm going to try to take 60 minutes, and I'm going to, that will leave some time afterwards for Q&A. There's a lot of words in my slides. I'm not intending to read those, you'll be pleased to know, but I can make the slides available in a PDF form afterwards if you want to contact me. My email address is on the screen. And of course, this presentation will be available for later review because it'll be recorded. So what are we going to cover today? First of all, we'll just do a little bit of background work to make sure we all understand how radiation patterns are represented graphically. We're going to talk about the effects on your station from soil conductivity, antenna height, and of course the terrain. And these things all have some interaction. I will use the examples, some of the examples from VE7NZ. There's a full-page report available. If you email me again, I can send you that. It's got 84 different analyses. So different antennas, different heights, different frequencies, this sort of thing in different directions. But I'll take a few of those from that presentation and show them to illustrate some of the points I'm making. I'll also take some other sites, some sort of things that we all wonder about, like, you know, what would it be like if you were beside the ocean? What would it be like if you're high on a mountain or by a cliff edge? And I'll do show some examples of those representations. And quite importantly, I'll show you how to use the HFTA software to do this kind of analysis on your station or perhaps a future station you may be thinking of. And we'll wrap up with kind of what are some of the conclusions. And I'll say up front, probably for every conclusion I make, there's somebody that will have a dissenting opinion or, well, it's not exactly like that. And that's true. You know, in order to accomplish something, you have to generalize a bit. And so we're going to make some generalizations in the interest of learning a few things. But if you want to get into the specifics, then contact me. We can always have some fun discussion and both learn something. Up front, I just want to say thank you to a few people that have, you know, I said to somebody today, really what I'm doing is taking a lot of information that other people have done, worked on and put together and efforts and learned from it and built on it a little bit, I think. Dean Straw, N6BV, is the author of the high-frequency terrain analysis software. Stu, K6TU, is I'll talk about his website that enables you to generate terrain profiles really easily. It's been a huge help. Couple of local hams, VE7JW and ST, who I've had some exchanges with, been very helpful. K0RV, who's got some great reference materials online. Another couple of hams, Mark and Gary, VE7RR, who I've spent time talking with about noise levels and their experience in working in some of the big gun stations around North America. And of course, a lot of material here I'm going to share is from the antenna book. I encourage you to buy it. The latest edition, I just bought it last year, and it is a huge upgrade on prior versions. And it includes the software we're talking about today. Okay, with that said, what could affect your DX success? Now, there's things you can't control. Obviously, the ionosphere, your terrain, the angles that signals arrive at your station. And keep that in mind. You don't determine the angles the signals arrive at. The ionosphere does that. You control what angles you can receive best. And soil conductivity. I'm having trouble speaking today. Okay, what might you be able to control? Antenna gain, height. You could stack antennas. You can change the phase in which you feed the stacks. You can increase your TX power. Of course, that won't help you on receive, but it'll help you on transmit. and where you buy your next home. How does terrain affect performance? Okay, I'm not going to read through all this, but I'm going to just illustrate it. On the right, there's two main factors that are involved. Well, three, I suppose. One is masking. If you had an antenna down here, you're just simply blocked by this hill. If you were right up against it, you're just not going to hear anything. It's masking all the signals. If you are back here a little bit, there's two things that come into play. One is diffraction. Diffraction is the reforming of waves behind an object. So basically, it's the, if you think of it as the radio waves getting over the hill and down to you, even though you can't see directly where they're coming in. The second one is reflection, which is a little bit more intuitive, and it's basically the radio waves reflecting off the ground and converging with the direct wave that you're receiving at your antenna. And it's this convergence that varies by frequency and height that is either destructive or creative to your signal. So depending on the phase, you'll get standing waves or you'll get nulls that add or decrease gains at various angles into your antenna. Okay, so let's talk about that a little bit. Let's talk about these angles coming to the antennas. There's two words you'll hear, arrival and takeoff angles. I think of it like airplanes. Arrivals are signals coming into your antenna. Takeoff angles are the angles that the signals leave your antenna. Thankfully, there's something called the theorem of reciprocity, which sounds super fancy if you want to impress somebody. Simply means it's the same transmitting and receiving. So if you can do the model for signals coming in, it'll also affect your transmit signal. Okay. I mentioned we do a little bit of remedial stuff here on antenna patterns. The one on the left here is your standard horizontal pattern that most of us look at when we're looking at antenna gains and looking at side lobes of our antennas and so on. Here's the one we look at a little less often, but we should, is the vertical pattern. So if you look at this pattern here, this is for a 3-element Yagi at a half wavelength above ground, and the peak is sort of somewhere around 28, 29 degrees is where the most gain is going. And there's a little bit of a out the back here as well. If I take this pattern, not this exact one, but something similar, and represent it like this, it's the same thing. What you've got here is angles from 0 to 34, and here you've got gain in dBi. So if you imagine taking this line from 0 to 34 here, it's basically this curve, just represented a different way. And we're going to use this graph on the right to represent these angles so you can see the peaks. This will make sense in a minute. Okay, a couple more diagrams. We talk in this model about, when we're modeling this, about free space gain. In free space, here's a dipole in free space, and other than off the axes, you can see it's donut shape of radiation. Where does ground come into play? As you start putting this closer to the ground, it effectively squashes that donut. So now it looks a little bit like this. And again, you can see your vertical patterns here, what the result is. Here's from the ARRL antenna book, various radiation patterns for a dipole at different heights, and going from 1/8 of a wave here all the way up to 2 wavelengths here. What you'll notice is that the pattern becomes more complex. It starts to, as you raise your antenna, yeah, it's good. Now you're getting your antenna lower radiation angles, kind of where you need them to be. But then, starting with D, which is your 3/4 wavelength above ground, you start getting some really funky stuff going on with little nulls, and it gets more and more noticeable as you get higher above ground. And these lobes can be great for gain, but there's also those nulls. So we have to think about that. Just going back to June 1970, I found this diagram. Why do angles of arrival and takeoff matter? Well, if I want to communicate 2,500 miles from here to here, I can do it a number of different ways. I can do it at this very low angle hop in 1 hop, or I can do it in 2 hops at a higher angle, or 4 hops at this angle. The truth is, though, every hop is approximately 10 dB of loss, plus or minus depending on a number of things. Let's say 10 dB. So this high angle shot here has 40 dB of attenuation, and you're simply not going to hear signals at that angle most of the time from this distant station compared to low angle shots that have less attenuation. So as a general rule, low angles are better. We'll talk about exceptions. Okay, let's talk about the software that we're going to use to create the models that you'll see tonight, or I use to create the models. HFTA by N6BV. It is included in the antenna book. They give you a code to download it ever since the 19th edition. What are the inputs that you can put into it? You can put in your frequency, your height, gain of your antennas. If you're stacking them up to 4 antennas, you can model for those of you with big ambitions. You can look at how you feed those, whether you feed them in phase or out of phase. You can put an input for conductivity of the soil, and of course the terrain, which is the big one we'll talk about tonight. But we'll talk about each of these inputs and explain how they affect the outcome. Okay, there's only 3 menus in the software. This is the main one. What you've got here is obviously frequency. Then you've got terrain profiles. I'll explain what those are, but this is basically saying that we want to see what the world looks like if it was flat. We want to see what the world looks like if we were taking a shot at 30 degrees azimuth. And then the number of elements in your antenna, and then the height. So really what I'm looking at here is I'm looking at comparing 3 different scenarios. What does a 3-element Yagi do when it's at flat Earth at 43 feet? What does it do if it's looking out over the terrain around my station at 43 feet? And what would happen if I boosted it up to 85 feet? And I can overlay those results, and we can compare and try to decide what's the right thing to do. We're going to talk a little bit tonight also about elevation profiles. What this is telling us if we're looking at the United States from Washington State, this file contains a representation of all the angles that signals come into Washington State from the US. I'll explain that in more detail coming up. Okay, the 2 other menus, just quickly, this is where you put in details about if you're stacking antennas, how high each one is. So you can do lots of different comparisons. And then there's the one about what the soil conductivity is and what your favorite measurement is, feet or meters. I think because we have some people from the US on tonight, I'll do a bit of both. Okay, so let's look at those inputs. First input, soil conductivity. I was on a net this afternoon, or just before coming here, and somebody was saying, I get great results because I live by salt water. And I thought, I wonder what kind of antenna he has, because vertical antennas definitely benefit from salt water. 5 to 6 dB. Again, these are generalizations. People can argue plus or minus from that, but definitely vertical antennas benefit hugely from good conductive ground. But if you look at kind of going from between salt water and the worst possible soil, that's what these graphs show. And at the angles that matter, like 30 degrees or less, here's 1.3 dB difference, 0.7, 0.9. It actually makes very little difference. And I actually modeled for this site the difference between salt water and average ground, and the difference was like 0.1 of a dB. So it just simply didn't matter. So big surprise, actually, for me. I didn't realize this, but yeah, high conductive soil doesn't make a big difference. It has some effect on horizontal dipoles at a quarter wavelength, and I believe that's related to the image antenna. But other than that, it's good for verticals, doesn't really matter on horizontal. Okay, next input you put in, the free space antenna gain. It's important to get the right gain if you want to compare between different antennas. The first thing we all do is go to our instruction, our spec sheet for our antennas, and we think, oh, that's good. This is my antenna. I have a Cushcraft X7, and these gains look pretty good. 12.5, 13, 12.9 on 10 meters. That's pretty good. And then I go and I look at a little closer, and it says at 1 wavelength above the ground. So I can get these as long as I can move my antenna up and down every time I change bands to 1 wavelength above the ground. So it's a little bit, okay, not quite great. I've talked to the designer of this antenna and understand the true free space numbers. But I looked at the antenna here, the Cubex Quad that Neil mentioned, and it's spec'd, you can find it in the fine print, at 50 feet. I'm not saying the manufacturers are being disingenuous. I just point out that you need to look at how they measure gains if you're going to do a comparison between antennas, as I've done before buying one. HFTA allows you to select gains or antennas from a simple dipole up to 8-element arrays. So it's pretty. It's got the full range of options. One thing I point out for some people think about, like my antenna is the X7, and so it's a 7-element array, but it's a log periodic log cell driver, so it actually performs more like a 3-element antenna, just very broadband. Okay, so we've got soil conductivity. Don't worry about it too much. And we've got antenna gain. Now we want to generate something called a terrain profile. That's what this is up in the top left. So what are we seeing here? What we're seeing here is an antenna that's 85 feet, up at 85 feet above the ground. If the world were flat, it would be this red line. Okay, the elevation of the of this particular, I guess it's the club here, is 200 feet above sea level. So if it was flat Earth at 200 feet above sea level, that would be the Earth, and this would be our tower 85 feet above it. This is the actual terrain, and I'll show you how we generate this. But if I'm looking at 30 degrees, heading is what that 30 means, this is how the terrain looks in that direction. Now, the terrain affects your signal up to 10,000 feet away. That's 3 kilometers, 2 miles. It's quite, I was really surprised by that. I assumed it would be a few wavelengths around me that would make a difference. But no, 10,000 feet. The scale is a bit confusing here because you're dealing with, you know, hundreds or tens and hundreds of feet here, and you're dealing with thousands of feet here. So it's, you know, you look at some of these and go, oh, I don't think that's quite how it looks around my place. But when you realize that the scales are so dramatically different, it's correct. I mentioned K6TU, Stu's website. Before Stu put this together, you used to have to do a fairly involved process to generate your terrain profile. I mean, people did it, but it was a bit of work using a program called Microdim. Now you can go to k6tu.net, sign up for a free 30-day trial, and put in your lat long, and you're immediately emailed a link to download 360 files from your QTH, one for every degree of the circle. Stu's site also does some things that once you've generated those files, you can also use it to do propagation forecasting for contests, which he bets me that if I was, say, to work CQ worldwide and then run the analysis afterwards, that he guarantees it would match my logbook, all of the openings. So I might take him up on that one day. And I forget how much it is, but it's not an expensive site to sign up for if you go beyond the 30 days. But this is wonderful because you can create profiles for your QTH. I did it for all 3 towers here. They don't vary a lot. I mostly focused on the 2 that were furthest apart, which is probably 100 feet maybe from each other, something like that.
Oh, no.
A bit more?
It's probably, what, 300 meters?
300?
Yeah.
300 meters, yeah.
From there to the
Yeah.
T3.
It didn't make a huge difference, though. It makes some difference, but, you know, don't get too fussed. I did some modeling at my place, you know, just moving the antenna around the property a bit, and it didn't make a big difference. Okay, elevation profiles. These are the files that go into HFTA that tell you what takeoff angles are most important, or arrival angles for working a particular DX region on a particular band. So how was this generated? They generated this using VOA cap and saying, okay, we'll set the threshold for considering a signal at 24 dB hertz. That's pretty much a weak CW, weakest possible CW reception. And let's run predictions between central Washington State, in the example I'm going to show, and Europe over that 11-year cycle, and see what angles those signals come in at. And then let's run it for Africa, and then run it for the US and South America and Oceania and Japan. So we get a set of files included with HFTA that include that data. You can create your own. There's a link here to how to do it, and I plan to do some work on this myself. But for those of us that are very close to the border, the club here is 20 miles north of the US border, the Washington State results are pretty usable. Okay, so this is an elevation profile example. Ignore the blue line, just look at these. What this is telling us is that at 14.2 megahertz, looking from W7 from Washington State to Europe, these are the angles that the signals will come in at, and the percentage of time they will. So if we look at here, say 5 degrees, that's roughly 10.5% of the time. About the same at 6 degrees, about the same at 4. Okay, we start coming down here, right here at 1 degree, that's 4% of the time, and so on. So you've got 100% here. So it gives you a sense of where the majority of the signals are going to happen over the 11-year cycle from that region at that frequency. So obviously, if you're designing how your antenna, how high your antenna should be for the terrain that you're in, you want to optimize it for where most of the signals are going to be. The more of this you can capture, the better. A couple of things about these elevation profiles. At the higher frequencies, the signals tend to come in at lower angles. So this is the same path to Europe. This is 20 meters. This is 10 meters. I mean, look at this one here. You know, what's that? 3 degrees, 3 degrees, and it's 35% of the signals are coming in at 3 degrees. And if you take a few of these, you pretty quickly find out half the signals or more are sort of 2 to 6 degrees. The other thing is the further away the DX, the lower the angles. And that kind of makes sense if you think of the earlier chart that I showed. Okay, here's Washington State to the rest of the USA on 10 meters. Here's Washington State to Europe. I mean, you're not going to see European signals coming in because of the attenuation that would happen at these high angles, but you will see them from a single hop on the US. I wanted to see how geographically sensitive this is. I mentioned we're actually not in Washington State, we're 20 miles north, so I thought, well, let's look at Oregon and Washington. So the one on the left here is Washington again to Europe, which you saw before. This is Oregon. It's kind of similar, There are some differences, though. It looks a little bit different. And that's only 250 miles apart. So I think if I was really planning a superstation or, looking at buying a property, I probably would run my own elevation profile for that QTH and really know that I'm working with the best possible data. But it's close enough for those of us, within driving distance of the border. Okay, so what if you don't have a whole lot of up and down in your terrain, like in VE5? We'll start with looking at the flat Earth results on HFTA because it's a good way to start things. So this is a 3-element Yagi, and I've got multiple curves. I'll break it down. The first one is the 3 elements sitting at 43 feet. So that's the dark blue line. So this is the gain over the various angles. And as you can see, the peak angle is somewhere here around 22, 23 degrees. And it's pretty good all through here, but they're way up here and kind of, remember that chart we just showed that was like everything was down around 8 degrees? So it drops off pretty fast once you start getting below about 12 degrees. So what if we move our antenna up to improve that? Get some of those lower angle lobes that you saw in the earlier diagrams. So the red line is 58 feet. Okay. Everything's just shifted a little bit more to the left, a little bit more compressed, a little bit more gain at the peak. That's good. What if we go to 73 feet with the same antenna? That's green. Well, now we're heading further left, which is good, lower angles. But we've got this null is shown up now because you've got those multiple lobes happening. What if you go to 88 feet? What happens? Now, again, even better, lower angles. And that's great if all the DX you want to work is down here. But look at this area here between 20 and 26 where you've got a lot of low gain because of this null. And if you want to work North America, there's a lot of DX or a lot of contacts in this range here. So that's a bit of a problem. So as Neil said, higher is not always better. It depends on what your goal is. So before we get into the really fun stuff with the complex terrain, if you're in a flat Earth situation, if you are in the prairies or such, I read an interesting article by Kai, who's I think the editor now of QEX, that he wrote in 2011, and he said for any single band between 7 and 29 megahertz, the optimal height tends to be around 1.5 to 1.6 wavelengths above ground for any particular frequency, any particular band, assuming your takeoff angles that you're interested in is between 2 and 16 degrees. Okay, that's great, but remember my multi-band antenna and moving it up and down. What do you do with that? Well, what he says is optimize for the highest frequency, like 10 meters in a tri-band Yagi, right? You will lose some of the low angle response in the lower bands on 20 meters, but you won't get the destructive craziness with all the nulls and so on that we saw. Well, we saw one null in the previous diagram, but the 10-meter performance won't be diminished as much as the 20-meter performance if you optimize for the high band. Again, counterintuitive to my worldview prior to this. I always thought, get up there for 20 meters, right? So, what if you're not in the Flat Earth Society? Let's take a look at the examples for this station that I will use to illustrate a few points. I won't read all this. I'll just say, there are 84 scenarios. Send me an email if you want to see all of them. Okay. So, Neil made mention of this. Pictures are good. On the left, one of the two Cubex quads sitting at 85 feet. And then on the right is the third tower, which has a TH7 at 60 feet and a 20-meter 5-element monoband or 20M5 at 85 feet. This is the terrain around the station here. For those of us that live here, it's kind of interesting to see how far away the terrain affects us. That's the 10,000-foot radius around us. Okay, so what is some of the good news here? The best performance was on 17 meters with the quad pointing to Africa. And here's a big reason why. Here's again our antenna. There's if the world were flat at 200 feet above sea level. But here's how it actually is. There's this terrain that kind of is bringing in a ton of reflections up into the antenna in a positive way. And you can see that on the left here, okay? The red line is if the world was flat. You'd have, at 85 feet, you'd get one of those nulls again, and you know, you're kind of capturing some of these signals. It's not bad. But look at this. This huge gain in this area here, okay, where there's the highest, pretty much the highest numbers of signals in the elevation profile. So you've got this really good low angle gain at 2 to 4 degrees looking at Africa. And I'll just, so you can understand the graphs again, I'll just quickly recap here, okay? We've got our frequency, 17 meters. We were looking at a heading of 63 degrees with the blue line, and looking at the terrain at 63 degrees versus if the terrain were flat. Okay, and the elevation statistic is these ones here, and it's from Washington State to Africa. So we're matching what could we do in that direction with what do we need in that direction. Now there's a very interesting figure here that is probably the most important thing. It's the figure of merit. The figure of merit is a weighted stat combining the gain and the percentage of signals at that angle across all of the antenna pattern. So the more gain you have where you need it, where these graphs are higher, the higher your figure of merit. So the reference point for me is always, oh, how would it be if the world were flat, right? If the world were flat, our figure of merit would be 9.1 dB, or dBi. But if you take into account the terrain, we're getting almost a 7 dB benefit from the terrain, which is fantastic.
The other factor in there too is that the higher wave angles are actually, you know, if you go back to that previous chart.
This one here?
So you take a look at the higher wave angles, and it's the antenna is still performing quite well within those ranges, which means even though we're looking at Africa, still within the United States, for example, where you'd expect higher wave angles, it's still going to be performing reasonably well.
Oh, yeah. Oh, I see what you're saying right here, yes.
And the null, which you see there is fairly narrow.
Fairly narrow, yeah. Yeah.
So overall performance would be pretty good.
Yeah. I would agree with that. Okay, let's look at the opposite case. And everybody that here at the club knows this situation. So there's our antenna looking into the side of a hill, basically, that goes immediately up 550, well, above sea level. So we're going up from our antenna up another 250 feet maybe. And that's extremely challenging. You're basically relying on, you're masked to JA, and you're relying on diffraction to some degree, which is the signals making it over the hill. On 10 meters, where diffraction is least capable, for lack of better words, I took that graph. So this was the worst situation. So now what you can see is flat Earth at that height is like this to JA, but just one second, just look at one thing. Yeah, no, okay. And then the blue pattern is the heading at 305 degrees. And we've got some pretty good gain over here, but it's all at, 24, 25 degrees where there's no signals, hardly ever in 11 years. So you're missing all this stuff down here, and you're capturing just a little bit right there.
But again, pretty good into the U.S.
The U.S. and South America are pretty good. They're about equivalent to flat Earth, maybe some improvement. I'll summarize that in a second, actually. Okay, so this one, looking at the USA, as Neil said, with the U.S. now, what we're doing, because it's closer, you've got a much broader distribution of angles, and you could use some gain here. And if you're in flat Earth, look, you're gonna miss out on all this stuff, and anywhere where the gain's starting to drop. Whereas you've got a pretty good pattern for that. Although it's not. What's interesting is it looks to me like the blue pattern is way better than flat Earth. But the difference actually, you look at the figures of merit, is only 0.7 of a dB. And you realize on closer inspection, well, you got this huge gain here, but you got a big dip in, like there's not a lot of signals in that gain point. And so all of that weighted average stuff adds up to about the same. About the same. Yeah, 1.5% of the signals are right here where this gain is. That's all. So what happens if we what if we wanted to get more of these higher angle signals and move this up a little bit? Let's go, what happens if we drop that antenna from 85 feet to 43 feet? Well, suddenly our figure of merit pops up to 11.8. So now we're about 2 dB better off by lowering the antenna. Now, would you do it? No, I wouldn't do it. We like the antenna to be up there, it impresses the girls. The other thing that this does not take into account is signal strength. So for us, signals from the US are going to be, pretty strong compared to signals from Africa or halfway around the world. So do you want to optimize your antenna to go from 20/9 to 22/9? No, it doesn't really make any sense. So that has to be taken into consideration. It's one of those things where you can overanalyze things and miss the real message. I mentioned diffraction seems to be more useful at lower frequencies, and this is an example of that. I modeled the situation here going to Japan. More work on lower bands. Yes, I figure of merit on the previous one. I have to look at again. But basically what happens is by going down from 10 meters down to 20 meters, you definitely get a better figure of merit. I didn't put the comparison in here, but it starts to improve. Now, it's still not great. But we're shooting into the side of a hill. I mean, it's almost an impossible situation, but you are getting into a situation where you're able to capture some of these you get some of these higher angle signals available to you on the lower bands, like 20 versus 10. And this was just comparing the 3 different antennas. One of the things I think can be useful if you're looking at different antennas and different heights and you want to kind of see how they perform is, I went through all the figures of merit for all 84 charts, and I looked anytime there was something more than 3 dB, positive or negative, and I made it green if it was positive because of the terrain and red if it was negative because of the terrain. No huge surprises given the scenarios I've showed you for the profiles, but it gives you a bit of a sense of, you can create these kind of graphs, and I've done a bunch of what ifs for my current station and my next station, and you can kind of see, okay, better off if I do this or that based on these things. Wherever there's no green or red, it was neither plus or minus 3 dB. Now, you could be quite concerned about 2 dB. I don't know. I try to look for a meaningful difference, and I think within the error margins of the models and various things, I wouldn't get too obsessed about 1 or 2 dB. Okay, how could we address that challenging path to JA? Just for fun, I thought, well, what if we took the 85-foot tower and moved it up another 50 feet? So the red line is the current situation at 85, 86 feet. And then the blue one is if we were able to add another 50 feet to the tower, what would it do? It'd improve our figure of merit by 4.6 dB, which is quite a lot. Now that speaks to a couple of things. Diffraction. You'll also see some examples that I'll show where basically the further you move back from obstacle, or the further you move either back from or above the ground when you have an obstacle in your path, even if it's 5,000 feet away, moving up helps, moving back helps.
Yeah.
Okay. This one I wanted to show because it's kind of interesting, and it leads us into a discussion about stacking antennas. I looked at this and I thought, okay, we'll take the 15 meter band and look at the USA. The blue is our quad at 85 feet, and the red is the TH7 at 60. They both have a figure of merit of 12.5, so they arguably are, going to perform equally. But if you look at it somewhat differently, you've got gain on the 85-foot antenna and a dip on the 60-foot one, and here you've got the opposite right there. So there's a few cases like that. So I thought, what if you combine those antennas? I thought it would be amazing, but it turned out to be about 1.6 dB better. It didn't really, or 1.4 dB, yeah. It didn't make a big difference. That's all that weighted average math there that's maybe not as intuitive as the eyeball. Okay, 15 meters to South America. What's going on here? The antennas, again, performing very similarly, identical figures of merit, but very different patterns. The 60-foot antenna being the red one. None of this matters, of course, because there's no signals down here. But this is kind of interesting. quite a gap in gain there. What if we could combine some of these things? What if we could combine these two and combine these two? That kind of leads to thinking about stacking. So I modeled this, and I said, well, what if you were to run, now they're on separate towers, so I want to get into phasing, and there's issues because if you were to stack 60 and 85 feet, they're a little bit too close, you need to get further apart. But let's just play the game and see what it would look like to stack this. Well, it gave a 3.6 dB improvement, because this is the combined pattern from stacking those two antennas, or feeding them together, if you will, even on separate towers. I actually played with it, and I thought, well, is more than 60 feet or more than... I played around with these numbers quite a bit, and actually, coincidentally, the heights that they're at seems to be the optimal combination if you were to do it. And again, you couldn't do it on the same tower, though. They'd just be too close. But that's one thing that could give you... 3.6 dB is not insignificant for improvement into South America. And then I ran a whole bunch of analyses and said, well, what other stacking combinations would improve things if you were to combine those two antennas? And it was 10 meters to Africa and South America, 15 Africa, South America, and 20 to Africa. Those all showed 3 dB or more improvement. Now, getting into, this is not an area where I have much knowledge, so I'm not going to speak much more about stacking, but, well, I will a little bit, just a little bit. But the other answer, of course, is just to switch antennas from time to time. If you're losing somebody on this antenna, switch to that antenna, or if you see which one picks up the distant station you're trying to get.
The other is diversity, right?
Yes.
So what I do on the Flex is, and also on the K3, is just run one antenna here, one antenna here, and it's amazing actually to see, as one drops, the other increases.
Yep.
So both the K3 and the Flex do a pretty good job of picking that up for you.
The other diversity trick that I've learned is I've got a 43-foot vertical, and even on 20 meters, it's just having the polarity diversity is huge.
Yeah.
Okay, this is not something I have much expertise living in suburban Vancouver, but I know that people say, okay, well, by theory, you're going to get 3 dB gain, and if you stack antennas, and if you have an antenna at 60 and 80 feet, the effective height is the middle point, it's 70 feet. This, you wouldn't stack at those heights, but you get the idea. So I thought I'll just play with the model and see if any of this holds true, and it did. Here's 45 and 80 feet, and there's the midpoint, the red one at 65 feet, and you can see, a few dB gain here, like pretty close to that 3 dB gain that you'd expect. And then what do we do over here? Yes, 45, 80 feet at, okay, so this was over a flat Earth, that's right. And then I took it at a 60-degree heading from the club here. And I just kind of looked at it, and sort of interesting. Yeah, you can see that the midpoint one roughly is the same pattern as the stack, or the effective point is the same pattern that you would expect from the stack. So kind of just playing with the model, see what happens. And then I look at a little stacking over flat Earth. So if you have an antenna at 45 feet, again, here's this. Remember the very early slide that I showed, and had that big null at 85 feet? Well, there it is again. But here's what happens when you stack 45 and 80 feet together. You get rid of the null. You take the best of both of them effectively. You bring the angles down, you eliminate the nulls. And I've talked to a couple of people who have worked with stacked arrays this in the last week, and they're like, yeah, that's exactly it. You get rid of those nulls. It's wonderful. Last thing I'll talk about stacking is if you feed the two antennas out of phase, you get a much higher angle all of a sudden. So the blue is out of phase stacking, and the red is in phase. And I'm told that some of the big guns have a switch. They can just flip the switch. They want to change the angle and see if it improves that particular signal. And cool, it works. Okay, salt water. A lot of discussion on this. I mentioned, well, this is not something about salt water. I mentioned that in the conductivity part. But I'm going to talk about setting up a station high over a cliff over salt water. That's probably the high over a cliff thing that's more relevant. So here's where we are, and my in-laws have a property on this island. That's nicely away from all these noisy people here and the RFI. And here's a picture of their backyard without the antenna yet. These stairs go down 65 feet to the water. And I'm kind of curious because I'm going to inherit this property one day, and I'm thinking, where should I put and how high should I put the antenna? And here's an aerial view, and I'm thinking, well, could it be near the cliff edge here? Should it be back a little bit? Should it be way back here by the back fence? So I did some modeling on these things. I'm very lucky. There's my father-in-law. My wife's a licensed amateur, but I didn't know about my father-in-law until he, over a drink one night, confessed that he worked for the Secret Service, for the U.S. intelligence. And he was a CW instructor and CW operator, wearing plain clothes, fitting in with the public, and by day and by night he was decoding Russian messages. And it's funny, he's 80-something years old now, and he can still come to my house and sit in my shack and sit down and just start listening to CW. And he hasn't I don't think he's operated a key in 50 years. It's just amazing. So I married into good fortune here because I think he's going to be all supportive of my experiments of this property. He wouldn't even show me that picture until a few years ago. He said it was classified. I said, we got stuff like that in the museum. Don't worry about it. So what does that cliff look like? Okay, so here's the property. There's another island here called Mudge. But if we take a look out over this line here where it's all open ocean, there's the profile, as you would expect, 65-foot drop and then ocean. So I modeled, I'm not going to go through more graphs because we've seen a lot tonight, or not on this one, but I modeled a 43-foot and an 85-foot tower at the cliff edge, and it made almost no difference in performance. What was happening was, because you're already 65 feet over the water, the extra height wasn't buying you much. It was helping a little bit towards Europe and the other directions, but it was actually making it worse in this direction. So then I looked at it and I thought, well, what are a few other things I could think about? Here's looking in this direction. So here is this island. Okay, so we got to get over that. And there's Nanaimo there, for those of you that know the area. This is the path to VK. And I looked at that and I found that moving back from the cliff edge to the back fence that I showed in the other one improved the signal by the figure of merit by 2.9 dB. And that was really an eye-opener. I thought, wow, I didn't expect that. And there is actually a button in the HFTA software now where you can say move tower back and you type in how many feet, and you can just go 10 feet at a time until you find that sweet spot, right? But this is consistent with the comment I made earlier that moving back gets you over some of these obstacles. So that's a good thing. So what did I conclude? And I could do a whole presentation just on that property, but cliffs are great. If you want to use a smaller tower, that's all you need. In fact, it's probably better. But then you sometimes tend to compromise in the other direction because now you're over terrain that's just 43 feet below you going in the other direction. So maybe you want to, again, if the water in that case is towards the U.S., maybe you don't care if you lose a few dB versus picking up signals to Africa. So you need to decide what you want to focus on. And I think, I look at it, and from here, we're pretty lucky. We have the Pacific Ocean. We have great signals over, the U.S. is close. We have pretty good pipeline into South America, it seems, and JA and Oceania, and that all comes in really well. These are all good places for us. So maybe I need to focus on Europe and Africa and not worry so much about those other locations. But lots more analysis, another few weeks. Okay, here's another example I wanted to cover. This is my QTH in Suburbia. All these houses are people inside them who wonder why their computers have voices coming out of them. And the ones I like, I tell and help them. No, I have really good neighbors. They actually help me put the antenna up. But it's a classic situation. You don't want to be too unpleasant to your neighbors. Half this antenna hangs over my neighbor's house, but it's a 40-foot tower, so roughly 43 feet, more or less. So I thought, well, what would happen if I added another 10-foot section to this tower? And it bought me. I have a similar situation to the station here, where the paths to the west are blocked by a hill, and it bought me about 2 dB. In that direction, good. But it also cost me the same to America and to the U.S. and South America. And I'm thinking, I don't know, for what that's worth and for the amount of beer I'd have to buy the neighbors, I don't know. One guy, when I put this tower up, this house up here, I walked up to try to do a sight line to north, which is where that's pointing. And I'm standing in his driveway with my compass, and I just moved in the neighborhood, and he comes out and he asks me what I'm doing. I tell him, and I found out he's the local bylaws officer. So I made friends with him fast. But anyway, the other thing that I wanted to, and I talked to Gary and Mark, VE7NZ and VE7NR, all the way around Mark and Gary, about this. And Mark said to me, he said, well, yeah, but if you move your antenna up, your noise level goes down. And that's important too. And I thought, does it? Does it? Not that I don't believe everybody, but I kind of did a bit of research on that. And it seems that if the noise is from houses very much under your antenna, yes, your noise level is going to go down. If they're a little further afield, less so. But I'm sure there's experts online and presentations on this topic. But I think it would be very interesting. And I think I have a reasonable suburban noise level situation, but I had a power outage the other day, and my 20-meter noise went from S3 to S0, and I heard stations I'd never heard before. So it might be an interesting experiment to see what it would do to raise your tower a little bit from that. So what would be the ideal situation? I'm driving my wife crazy because we were going to bed the other night, and I said, I got to get up. And I just thought of something I haven't modeled. So I wanted to see, what would be the perfect house? What would be, and I envision it must be sitting on a cone, like on the right there, where you basically got the nice takeoff angle in 360 degrees. So I started plunking in numbers left and right, and I came up with, and there may be somebody that has more time and get more precise, but it looked like about a 2,000-foot height and about 6 kilometers across the bottom, 4 miles, would be just about perfect. And of course, that terrain profile looks like this. And if you had a house called the House on the Volcano, this is what that pattern looks like. So this is a 43-foot tower, 3-element Yagi, and this is flat Earth, and this is the benefit of being on a cone. And that figure of merit difference is like, what is that, 9 dB? 9.2 dB difference. That is where you want to live.
It's interesting because that's actually what drove Dean Straw to write HFTA. Dean Straw.
Yeah, because he was looking for a place, the ideal place.
He had a place, and he was finding that the taller tower actually didn't benefit him to any great extent,
right,
whereas something lower did. So he tried to understand why that was, and the outcome of it was HFTA, as I understand it.
He's got some good presentations online. You can watch too. It's been very helpful, and he helped answer some questions on email. So I just took a look for fun. What about 10 meters? I mentioned things get a bit wacky as you get higher at the higher frequencies, and they do. But fortunately, all the wackiness is, well, it starts to drop off a bit here where there's some signals, but there's a null here where there's no signals basically. So it's still pretty good. You still have an improvement over flat Earth of 3.6 dB. So. And that's a path to Africa. I picked kind of the furthest away. So that was fun. So then, before I went to bed, I did a little Googling. And I went back and I said to my wife, I found a place. I said, look, it's got the mother-in-law's suite here. It's waterfront. It's away from RFI. It's perfect. So she said, good luck. Send me a postcard. This is a house in the Mojave Desert. It just sold for $750,000. It's really cool inside, but it's not 2,000 feet, so pass. It's just the closest I could find on a quick Google. But I was thinking, I used to operate at Burnaby Mountain, VE7NZ, and I was looking at Grant Hill up here, or Thornhill.
Yep.
There's some places we need to annex.
You bet.
Okay, so what are some of the limitations of this software? Okay, first of all, it's for horizontal antennas. That's when I say limitations, these aren't complaints. You just know what it does and doesn't do. Okay, it's for horizontal antennas. It's for up to 30 megahertz. I've read some guys online that say, "Oh, it works great for 6 meters." Maybe it does. I don't know. It's not spec'd for that, so I don't know if that's a fair comment or not. It is a model, and there's got to be some margin of error in this. I would not obsess about a couple of dB. Look for 3 dB or more before you start making any decisions. You can get artifacts in the results. You can get some nulls that shouldn't be there, things like this. If you're actually looking at where to put your antenna and investing the money, experiment with adding a foot here, subtracting a foot there. Just make sure that the results migrate as they should, that you're not dealing with some anomalies. Just do some 1-foot increments. The other thing is, things have changed a bit since all those elevation profiles were done on CW signals. FT8 is 6 dB better, signal noise threshold. And then, JT9, 12 dB. Sideband, depending on your filter, let's say, is 16 dB worse than CW. So let's say you don't care about digital, you don't care about CW, you may want to run your own elevation profiles just on the threshold of, like 30 or 40 dB hertz, because you only care about signals that you're going to hear on sideband. And those might not be the lower angle ones as much, because they've got more loss because of the multiple hops.
Just talking about saltwater, horizontal, and vertical antennas. I've done a lot of de-expeditioning out of areas that are adjacent to salt water, Indian Ocean, French Polynesia. We typically always use vertical antennas within a quarter wavelength of the water. And I've actually, down in Lakshadweep Islands, we compared a 2-element stepper to just a simple vertical that we had located at the water's edge. And there was a 20, almost 30 dB difference at certain times of the day into North America from India. It's quite phenomenal. So, for those folks who, are adjacent to salt water, and I mean right close to it, verticals are also a very good, one of the reasons being they have a fairly, even approach to all of the wave angles as opposed to the sort of jaggies we're seeing with the nulls and the peaks on horizontal antennas. So I can speak to the vertical stuff because I've used it extensively, and it's good at saltwater. But having said that, inland it's not as, it gets stomped by good horizontal antennas at the right height.
Yeah, I've seen that it's very popular on these islandy expeditions for that reason.
Well, for a lot of reasons too. It's easier to carry a vertical or just a wire that you put up as a vertical.
Yeah. Good. Okay, so try this at home, folks. Buy the antenna book. Even if you don't do this, I got to tell you, I'm nerding out on the new edition, with, volume 1, and just reading through it. It's just really, really been, probably my previous one was 15 years ago or something, but it really you think antennas haven't changed a lot, but there's a lot of new knowledge and new designs in the latest book. That'll give you this software and a whole bunch of other things to download too. I recommend Stu's site a lot. He actually, should thank him, he fixed, there was a problem with generating profiles if you were too close to the Canadian border, or the US border rather. And so he wrote some code to properly parse the call signs and generate the right profiles for us, so thank you. Figure out your free space gain. Use that. That can be interesting to work on. Probably choose average soil conductivity if you don't know. It's not going to make a lot of difference. There are maps. There's online maps. They tend to stop at the Canadian border, unfortunately, but you can get the soil conductivity numbers off of Google for the U.S. And then start experimenting with what ifs. Like once you start, it's like, what if my antenna goes up this much or down that much, or what if I stacked it, or what if I did this? It seems like I've been playing with this now since about Christmas, and every few days I think of something else to figure out. Do create your own elevation profiles if you want to be really precise, especially if you're far from the border. We get away with Washington State, I think, here, but if I was up north in Prince George or somewhere, I'd probably want to do my own profile, because I think some of it would be different. Or if you want to look at particular regions of the U.S., what is all signals from the U.S. to somebody, here, if your focus is the California CUSA party. Right. So, what do we learn? A few conclusions. Flat land is the easiest to optimize in all directions. I would say uniform land. Our cone on the hill is also a case like that. But, barring that, basically flat land. Stations like K3LR have that to their advantage. It's great. They can optimize in every which way. Everything is a compromise when you live on a hill. Gains in one direction are losses in the other. So choose your battles. Choose what you want to focus on. Living on top of a gently sloping cone or the edge of a cliff, things like this, shorter towers are just fine and probably preferable in many cases. An oceanfront property is beautiful, but it may not improve your signal if you're horizontally polarized. Think about contesting and hunting DX in different ways. If you're in Colorado, you've got stacked monobanders, and you've got a very narrow beam width. You might have a nice low, you might have the right angle you want, but you'll be spinning the antenna constantly trying to work everybody. And sometimes, I know Neil's talked about that here with the 20-meter monobander being just super narrow for North America sometimes, right? But if you're trying to get an all-time new one and bust a pile up, different story. So think about the context, what you like to do. More gain doesn't necessarily help. If you're at the wrong height, and you know, if I phase two antennas at the same height, I'm just gonna have more of the same nulls, right? And again, it can make your narrow, your horizontal pattern too narrow. I think we kind of covered that. Again, decide your goal. Are you looking for new ones? Are you looking to bust pileups? Are you looking to have run in a contest or search and pounce? All these kinds of things. And I would just say at the end that, you know, despite one of the things, it's a bit depressing actually, get into these figures of merit. And you start thinking, oh gosh, you know, this is not good and that's not good. And if you looked at the tables for my station and here, you would think we'd never work a station in Japan. You know, almost impossible. But we do. And, you know, I've got DXCC on 10 to 80, despite my situation. The club here does wonderful. You know, it might just take you a little bit more time than other stations into some regions, but you'll get there. And don't get obsessed. It's a model.
It's your dream house.
Yes, that's it.
Yeah.
And then the last thing is just if you want a PDF of the slides, I've got, a whole bunch of reading here on articles that I read and found on these topics and presentations online. So you guys can, you know, there's a lot of reading on the different related topics here: antenna heights, soil conductivity, elevation profiles, all that. And with that, I'd like to say thank you to Club. Thanks, Neil, and thanks everybody for inviting me. This started as something I just thought I'd do for fun, and then I got asked could I present some of the results, and then it turned into teach people how to do it. So hopefully some people found some value in it.
Well, thank you very much, Adrian. I mean, this has been tremendous. I think it's been an eye-opener for many of us. I know you and I have talked about it extensively over the past few weeks, and certainly we got some ideas on how we might.
Give him a hand.
Yeah, well, absolutely, sure. How about a hand? Yeah, we'll have a virtual hand from out in the ether. So.
Thank you.
It deserves one.
Yeah, but thank you very much. So, are there any questions for those of you on YouTube or on video? Please feel free to type your questions into live chat. And let me just see here. I have to look very closely to see, but I don't see any questions at this point. How about in the room? Anybody with questions? Alex, I'm sure you have questions.
I have questions because I did a lot of research. I actually used an antenna optimizer they offered in the package, Turner Analyzed software, which does same things but a little bit more rudimental. And when I was in university, I was just running like simple, like kind of spider beam with fishing rods. And I used to go on top of, I tried different kind of situation. And I did like simulation, and then I went on field. So top of the hill, and I say, great, front of the ocean, top of the hill was good. I start like close to the ocean, and it was, okay, good. And then I went the top of mountain, like 2,300 meters above sea level. So ground wave was huge, but the X not really good. And then I found the best location was a cliff. And I went, this cliff was like 45 meters above the ocean. It was Adriatic coast in Italy. And then it was like really amazing to see how strong were the signal comparing to local stations in my area.
I see.
So I was a guy, especially on 10 meters. 10 meters, huge. 15 meters, good. 20 meters, start like signal pretty, not very different from other stations, but 10 meters was impressive. Because I remember a guy using a monoband 5 elements, and I remember station from Guam or Japan or VK, ZL. So when same power, my signal was S7, S8, and S9. His signal was like S2, S3. So 6 S points difference. And he was just in the same city. It was just by the ocean, but like 2-story house and antennas. You know, the difference was really huge. So, and you just demonstrate that on 10 meters, low radiation angles are really,
Yep.
you know.
Okay. Thank you, Alex.
You're
And I'm
welcome.
glad to
That's
see.
right.
I'm glad to see you're wearing clothes as well too.
Yeah.
Just for those out there, Alex tends to be half naked during our Zoom monthly meetings. I'm just kidding, Alex.
Okay.
Got the wrong meeting.
That's right. Half of us appreciate it, right? Yeah, exactly. I'm not so sure. Listen, we have a question here from VE6 Fox Tango Papa, and he's asking: is this modeling software useful for near vertical incidence antenna planning?
I would say no, because it cuts off at 34 degrees. It won't give you any performance data above 34 degrees. And for NVIS, you want obviously close to vertical.
Okay.
They're 80 degrees.
All right. Another question here from Rodney. I'm not sure what his call sign is, but Rodney has a question. How did you measure the data for the angles of arrival statistics with the 1 to 2 degree accuracy?
I see, yes, because it's like increments of 1 or 2 degrees on the graph. Yeah, I didn't do it. That was done using, that is provided to you by HFTA, where they run, somebody has run models in VOA cap to determine the, to calculate the angles of arrivals. It's not actually listening and recording angles. It's modeling what those angles would be in VOA cap. That's how it's done.
And the modeling has been done for designated areas throughout North America.
Yes, each state.
Each state, not Canada, but each state.
Each state and into each of the, what was it, 5 regions, Europe,
5
Africa,
regions
and
of the world,
yeah.
So all of that work has already been done. For those of us sort of adjacent to the border, it doesn't matter where we are across the country, but we can use the nearest U.S. state to us, and the results should be relatively close to what we expect. Okay, if anybody else has a question, please turn your camera on Zoom so we can see you. And we'd like to bring you into the meeting. So here's your chance. While we're waiting for that, is there anybody else with a question in the room? Aaron, do you...
I'm good right now. I'll think of a few. Give me a second.
Okay, fair enough.
What can we do here at our station, given all the information that blew me away, to optimize our antenna systems?
So, to crank the tower up or down is not an option for us.
No.
But what is an option is, as Adrian was pointing out, is to combine, depending on the area of the world that we're looking at, is to combine, say, the TH7 and the quad. So not phasing them necessarily, but
'Cause they're
even
far
using
enough apart.
diversity, which the current rigs we're using all have that capability, makes quite an amazing difference. Now, the issue with the TH7, it's great for the Caribbean and for South America, but it's not rotatable, right?
No.
We have it in a fixed location on the tower. But, one of the options would be there to look at how we make it somewhat rotatable by an extending arm.
Yes.
That's one of the options down
Sure.
the road. The second is, for example, I've got a 10, 15 meter dual bander, which might work, say, at 50 feet on the T1, right?
Yep.
And it would, cover those areas at higher wave angles within the U.S. and other areas of the world as well too, but primarily for into the U.S.
So we need to explore combining antennas
Yeah.
on the two
Yeah.
antennas that are towers that are 300
Exactly.
feet apart.
Yeah, so our situation is we've already made the investment in the towers and the antennas. Everything's up in the air, so how do we tweak it to make
Yeah.
it better? For somebody who's actually planning a system or has the ability to modify their system, the type of analysis that Adrian's gone through here is invaluable in terms of
Invaluable.
sorting
You
out
betcha.
what area of the world you want to focus on,
Yeah.
and given your terrain,
Yeah.
the kind of tower and antenna that you would look at.
Tell Keith to fix it.
Absolutely, absolutely. All right. Anybody else with questions? Oh, we have a question.
Good evening. Awesome presentation. I might be splitting hairs a little bit here, but if you have substantial buildings nearby or in a highly dense urban area, does that have any meaningful impact, or again, am I just splitting hairs?
Well, obviously noise is one factor, but as far as the physical presence of those buildings, I have not thought about that. You know, it's presumably, as with any obstacle, I mean, if it's big enough, I noticed some effect from one of the paths we have here where we have a 50-foot protrusion of land, like it's 50 feet above what would otherwise be, you know, the level the tower starts at. So it's a little bit of an obstacle. And it looks to me like it's causing us a little bit of a, you know, maybe costing us a dB and a half or something like that. So I think the answer is probably yes, you know, when I look at that. Of course, buildings have a different kind of RF characteristic than Earth.
The magnitude of the impact would be really how it sits in front of the, you know, the aperture of the antenna. So if
Yeah.
your antenna is low and, you know, your antenna is 40 feet high pointing into the side of a 50-foot building, there's going to be, you know,
Yeah.
a lot of impact from that. But with the towers we have here in the building that we're currently in, we're well above it. So yes, I agree that there's probably a little bit of impact, but the impact is probably quite negligible given how close this is to the towers, particularly to Tower 2 is right beside it. So the answer, Bob, would be yes, depending on your circumstances and how close and how high the antenna is compared to the building that you're adjacent. For buildings at distance, it's hard to say. One of the things that Dean Straw came up with, and he used a lot of ray tracing to look at you know, what the near field and far field impacts were when transmitting. And he found that, you know, a great big boulder, you know, would have, based on ray tracing, which is not real world, but it's modeling real world, did have some impact at the endpoint that you were transmitting to. But there was some cancellation associated with that. But the reality is it's probably not that significant unless it's a really big building.
I think another factor that I think about where I am, you saw the photograph, I've got, you know, I'm at 40 feet above my neighbor's house, and for the second story of my house and the neighbor's house is like 12 feet under the antenna. So that's another factor that
Yes.
I know that's got to be affecting my radiation pattern in
Right.
not the best way.
Yep.
They're wooden house.
It's a wooden house.
Yeah,
Yeah.
but there's a lot of metal in there too,
Right. Yeah.
you know,
Yeah.
aluminum siding.
Okay. All right.
Burn it down with RF.
Oh, VE6LK, welcome.
Good evening, Adrian. Thank you so much for an awesome presentation. So is there any hope for guys like me that have a vertical and want to do the same sort of analysis?
There are some articles on this in that list that I have at the end of the presentation. There is one, and I think it's again, I think the June 2011 QST article by Kai, KE4PT, I think addresses verticals, if I'm not mistaken, as well. Talks a little bit about the effects. So, I mean, verticals by their nature automatically have a lower radiation pattern if you have a proper ground. Right. And that's actually extremely useful. I have that 43-foot vertical with a tuner that I use on 80, and I can hardly hear most of the BC Public Service net signals. If I put on a magnetic loop, I can hear them all perfectly because it's got a much higher angle. But for DX, I can use that wire to work, you know, Australia on 80.
Well, one of the resources you might want to look at is John DeVolder's book, Low Band DXing.
Yeah.
And he does a tremendous amount of work in looking at the impact of ground planes on verticals, particularly on the low bands. And he also has quite a treatise on whether you put in 120 radials at ground level or you elevate radials, and some interesting results from that. So, you know, that would be. You're shaking your head, so I think you've probably already read his book, but.
Oh, no, I haven't read his book, but the matter of how many radials can almost become a religious discussion depending on who you're talking to and what day of the week it is. So I appreciate that there's some good data in behind it.
Well, you know, I can tell you from personal experience, you know, operating out of Lesotho in the middle of you know, a very dry area we were at about almost 6,000 feet above sea level. with flat out to most areas of the world, but there were some hills in the way. We had Yagi antennas that we used quite a bit, but I'd brought a 30-meter antenna vertical and also a 40 vertical, and then we fabricated an 80-meter vertical, which we also pumped onto 160. The K4SV, who was my de-expedition partner on this, kind of poo-pooed verticals. He's a Yagi guy to the max. After that de-expedition, he was a convert, and I used 4 elevated radials for 30 meters, and it was an absolute storming antenna. We laid out radials on the ground for the 80-meter and 160-meter. In the process, we damn near set the field on fire. We actually did have a near incident from that, but that also worked quite well. In fact, from the middle of Africa, we worked 3,000 people on the west coast of North America. So, that kind of tells what that level of performance was like. But I can tell you, on our last trip down to the Australs, we used wire antennas, which were verticals with 2 radials each, and they did extremely well, TX5N.
Yeah, elevated radials are, you get it right, quite effective. The other thing that's interesting, when I put up my vertical, I took measurements every so many radials that I put down and plotted all the changes in the performance of the antenna, the radiation efficiency, and it's fascinating to see. And you start to see, big changes, and then it starts to diminishing returns, right? So you decide at what point you're going to stop running wires through your wife's flower bed.
Just as an aside, kind of a humorous aside, before we headed down to Clipperton Island, I built an 80-meter vertical, which we actually put just up the hill here, and used a couple of elevated radials. And you probably remember there was a big argument about, well, the SWR is really good, and I'm going, it shouldn't be, right?
Yes.
So until you get those elevated radials decoupled from ground, which on 80 meters it means should be up, 8 to 10 feet, then you get SWR that's more representative of, 35 ohms, I guess it is.
We were amateurs at the time.
Well, we still are, to be honest with you, Wayne. So just, a little bit of feedback there. But DeVolder's book is I found was really informative.
Very good. Thank you.
You're quite welcome. Anybody else?
There's nobody. I had a quick question.
Yeah.
Aaron, Victor Alpha 7 Zulu Alpha. Just wanted to find out, you were mentioning the 3-element Yagis you talked about in most of your examples using the software itself.
Mm-hmm.
How many different antennas does the HFTA cover? And second, can you make your own antennas in the program?
9 antennas, so dipole plus 8-element array. So I guess there's actually 8. 8 antennas. So you can go from a dipole to a 2-element Yagi, 3, 4, 5, 6, all the way up to 8. But it specifies, the second question is no, you can't input the gain manually, but you can, if you have an antenna, and I played with this, so if you have an antenna that's performing at a certain free space performance, and it doesn't quite line up with, you've got this many elements, but it works out to this amount of gain, just find the equivalent antenna for that gain, so you get the right gain in the model.
Does it have any models for switchable vertical dipole arrays? SVDAs?
No.
Yeah, it's a shame.
All horizontal.
All horizontal. Okay.
Thank you.
Okay, any other questions? John Livingston, thank you very much for your compliments. He says, great presentation. Thank you.
Thank you.
If you had to do it all over again at your current QTH, what would you put up knowing what you know now?
I don't think I could do better than I've done. I think I've got 11 antennas on a suburban lot, and I've got the neighbors pushed to about as far as they'll go. And
the
I mean,
municipality.
I know what I would do. I've already told my wife if she dies that after the funeral, I will put the antenna right in the middle of the backyard where all her gardening is, because that's a better spot, and I could easily go higher, wouldn't bother anybody, and there'd be
That's sacred ground, is
right.
it?
She is. I'll never say a bad word though. She's very supportive of my hobby, and
Wow.
she knows how much I enjoy it, and
She has a call as well.
she has a call as well, VE7NZ, and
DDS.
if you work her, she's on the air once in a while. You get a special commemorative QSL card because it's a rare event. But she gets on once in a while, and we have a lot of mutual friends that we hang out with, and every now and then she'll check into a net just to throw somebody off
Yeah,
key.
yeah.
Your son is licensed
Yeah,
as well.
VE7NZ, yeah.
Very good.
Yeah,
All right.
and my dad and my cousin and
The whole world
my
is
former wife
licensed.
and-
Your former wife. And
yeah. I'll stop there.
Which, I was going to say which farmer way. Okay. All right. Well, I think we've come to the end of the questions. Just looking around the table here. Okay. Well, listen, this is, I think it's turned out very well. And thank you very much, Adrian, for all the work that you've put into this. And certainly a lot of your findings, I hope, will be able to integrate some changes that will make a difference here at the club. And we're very fortunate to have what we have. And just for those of you out there, I did a little preamble at the beginning as to what the club is, but what we've done here is we've put together a station that is available for all club members to use on a 7x 24-hour basis. So there is a pass card system that people can use to get in here, and for equipment that's available at that time after being trained on how things work. Because you poke the wrong thing into the wrong place, you're going to have a smoke test, right?
Yeah.
But yeah, exactly. So it's available for those people who really don't have the opportunity to operate from home anymore. Maybe empty nesters have moved into an apartment, or people like me that's not an empty nester, but I live in a condominium that doesn't allow stuff to be put up on the roof. We do have 2 radios here which we operate remotely. It's the way I operate most of the time. Ian also has a remote setup with his NN, which is also an SDR. And soon we'll be remoting one of the K3s. So, we do have a capability of coming in from the outside. But now that COVID is over, I expect we'll see considerably more usage of the club equipment, and we're looking forward to actually people beginning to come in and take advantage of it. If you're interested in finding out a little bit more about the club, go to our website. Any support that you're interested in providing, you can find the information on that site. If you have any ideas for future presentations that you might be interested in, fire them to us. We'd be happy to take a look at them, and maybe we would be able to put something together. I just wanted to also thank Ian, VE7HHS, Phil McCormick, VE7KGR. Those of you that are on the BC Public Service Net probably recognize him as the nation's station. VA7ROH, Matt Dodge, and Daryl Hahn, VA7EDR, who are really the production team here. If you saw this room from behind the cameras,
It looks like a TV studio.
It's like a TV studio with switching and a very professional audio system that Phil has uses for his work environment. He works in the television and movie industry, so we have mucho equipment in here, and I think it seems to have worked quite well. The YouTube feed, by the way, is about 30 seconds behind the Zoom feed, but is fairly high quality. It's 1080p. The entire presentation will be posted to YouTube and available for viewing in any part of the world if you so choose. Just looking here, a few kudos. My goodness, lots of stuff here. So VA7QCE says, thank you, Adrian. VY1YU says, many thanks for an informative session. So hi to you, long distance away. Let's see, VA7GI, thanks, Adrian, great presentation. I have hope for my low beam now. And V6 FTP, to everyone, great presentation. Thank you very much. So really appreciate the feedback and the comments, everybody. And well, we'll look forward to maybe another presentation down the road. Thanks very much.
Thank you.
Thank you. Great stuff.
All right.